As Claudia said, I will show you how we show a small sample tracking script to control our Luxendo microscopes. And here, I think the focus is not really how to do the tracking, but how to control the microscopes. And I will show you a little bit the architecture of our software and the API, how it works. And then we'll have a little hands-on, I mean, the remote session with the real microscope to see it in action. Hopefully it will all make sense. Yeah, so of course, we provide the microscopes to our customers, but that's normally not enough because people want to do imaging and get some information out of it. And there are multiple parts of that workflow. So of course, the first one is to have a computer talk to the microscope, record the images, and provide an interface to the user. And this is all controlled by our acquisition software called LuxBundle, or the user interface is the Lux control. And in the same interface, we also provide visualization for the recorded images and as well as image processing. So this, for example, for the movie spin, where you have multiple views to fuse the rotated views and the opposing cameras together, or if you have a large sample tiling, then stitch the tiles together. And all of this also nicely ties together with the Aquifer Hive. So as Lauren said, Aquifer has been part of Luxendo as well for a year now, roughly, and this way we can also provide fast compute and storage solution, and basically everything is connected to this central computer, and there are many different parts of this software. All of them working together, but they're very well containerized, so they're all their own entity. And how we do that is it's actually pretty important that we do that, because we have very diverse product portfolio. So this is just a snapshot of all the different microscopes that we developed throughout the years, but we have 4 main families. And I'm not going to go into that, just wanted to show that basically we have the same software running for all of these, so it's very modular. So the way you do it is that we use the MQTT protocol to talk between the different components that I showed on the first slide. Maybe some of you have heard of it, but I will briefly explain how this works. So this is an open standard for IoT communication. It's network-based, so based on TCP/IP, and it's a publisher subscriber model. So basically, there's one broker in the middle, kind of like a server, and multiple clients can connect to this broker. And what the client can do is that they can publish messages, typically their own state, under a certain topic. So each client will have its own topic, and under that topic, they will publish messages to the broker. And then other clients can also subscribe to these topics to receive the messages from other clients. So basically, each client can decide which other clients is interesting for it, subscribe to those topics, and then the broker just takes care of sending the messages around. So I hope this makes sense, because this is going to be pretty important for the API, how it works.
Maybe if I can just have a quick question. Was this the first solution that you visited? Was it this because you tried others and they had issues that this one solved? Like how did you reach this conclusion, let's say?
Yes, originally we had more like a peer-to-peer model between 2 components. So one component running on the microscope. So in the microscope, we have a small embedded computer that only connects with the network to the outside. And then we have the user interface. So initially it was just peer-to-peer connection. And then as we added more and more functionality, more and more components were included. And then we thought that this publish subscribe model would be more flexible to handle that. Yeah, so actually this is how it looks in our case. So So we have this backbone, which is the MQTT broker, and then the different components are this embedded that I already mentioned that sits inside the microscope and controls all the hardware. Then we have the user interface, which we call the Lux control, an image processor, data hub. We have an updater module that updates all the components. We have some SLM control, and basically, because it's a very modular way of talking to each other, then people can also write their own scripts and write their automation scripts to connect to this by connecting to this broker. It's very flexible. It's relatively simple to extend it, and basically this because this whole thing goes through the network through MQTT. Basically, any language can be used to implement any of these components. So for example, this embedded at the moment it's in LabVIEW. These two are in Rust. Lux control is a website. So you can use whatever language you want as long as it has an MQTT library. And most big languages do have MQTT library, and you can use it to write your own script to connect to that API and talk to all the other components. Just an example how it looks like in practice. So we use JSON messages. So send these through MQTT, and yeah, we like this format because it's easy to read, easy to write, and easy to parse by machines as well. So for example, when the user interface starts, it will publish a message to this topic. So this is the serial number. SN is the serial number for the microscope / GUI. And it will just say that, okay, it wants the system capabilities. And then the embedded systems subscribe to this GUI topic. And then it sends a reply to this embedded /system topic, and then it lists out all the components it has. And this way, the user interface then knows how to populate the different panels. Yeah, so I think, yeah, about the sample tracking, I mean, it's nothing crazy complicated. So basically what the script does is that it monitors the acquisition to detect if a new stack was recorded. So basically it does that by subscribing to this serial number /data /cameras topic. And here it can receive the events from the cameras, and one event is about saving the images to the disk. And then once it has the next time point, it can compare the sample position of the previous time point using some fast FFT-based registration. And from this registration, it figures out the drift compared to the previous time point. And if drift is above a certain limit, then it adjusts the stack coordinates, and then this will ensure that the sample will keep in the field of view. So I think this is hopefully it makes sense. I think the whole tracking concept is I think it's not that complicated. Basically, just compare the two time points, see how much shifted, and then change the coordinates in your stack definition. Any questions until this part?
I have one, yes, actually. For the event for the stack, is it like a different event if you like for just a plane, let's say, when the camera is done acquiring a plane, and then if you're done acquiring a stack, do you have like different type of events?
Yeah, so we have when you run the experiment, we always take a stack, and so if the microscope is under automation control, then everything is a stack. In live mode, you can have events for single planes, but that's normally just during when the user is also interacting with the sample when they set up the experiment. So during the experiment, it's always a stack of images that are recorded.
Maybe another question. So, I mean, you can create potentially very, very large volumes, right, with your system.
Yes.
So then within one time point at the next, I guess that you could have synchronization issues if you are still running your analysis routine. Is the strategy here to optimize the routine to run as fast as the acquisition, or that once the, like you can have a few time frames and, potentially kind of send instructions once the analysis gives you some feedback? I mean, what is the strategy there for synchronization?
Yeah, exactly. You're right that data can be very large. So there are two ways. One is basically making sure that just do a test and ensure that this registration is fast enough. And then the other option is that you don't need to do the tracking or this registration every single time point. You can do it every second, every third time point, and this is configurable. So maybe we do a little practical.
Balint?
Yes.
Just out of curiosity, so you do FFT-based registration directly in 3D, or you do it like
exactly
separately
in the 3D dataset? Yes.
So you basically calculate like correlation on 3D data directly.
Exactly. Yeah. So we downscaled the images so they're not so large. Just for this tracking purposes, that's fine if you downscale it by a factor of 2 or 4. And then I think this is done on the GPU, this FFT, so it's quite fast. And yeah, and basically you just get this cross correlation from this FFT, and then you just get the vector from the points from the first time point to the next time point. And the nice thing about this is that you don't need to know anything about your sample at all. It can be anything. So it doesn't need to have a nice boundary. It can be just the middle of a big tissue.
Maybe just maybe as we touched on that, so I agree. So there are some cases where you simply cannot know about the sample, but in case the sample changing its shape, right? Is it like something where you say basically which part of the sample to follow, right? Or it's just following the entire
yeah, at the moment
view, right? Because if there are like structures migrating inside the sample onto your interested, like, I don't know, in particular group of cells, probably what would be relevant in your project.
Yeah, that's a very good point. So at this point, we only look at the entire field of view. Of course, it would be possible to restrict it to certain parts or give it some more intelligence. But I think the point of this demonstration is more to explain how to talk to the microscope and not the image processing part. So of course, yeah, you can just swap it out to some smarter algorithm to make it better, and the rest of the pipeline should stay the same.
Sorry, it's just because I'm very interested to this idea that you said that the user can just quickly test that the speed would be enough. So basically, you have some kind of inbuilt unit test where you kind of, by knowing roughly the size of the data that the user wants to acquire, you kind of check that the hardware is capable of giving you an answer within certain time frame, and that is giving us feedback to the user in the user interface. Or how do you do that? For some reason, I lost your audio.
Okay, I'm back. Somehow my
Yes,
headphones got disconnected.
No.
Yeah, I mean, we just have in the script some basic diagnostic log that tells you when the registration is finished, and then you can just check if it's done before the next time point. So it's kind of low tech, but it works. And normally it's comparable to the time it takes to acquire the stack. So typically it's no problem to run it with very fast time lapses. Because of course, the more planes it takes, the more it takes to acquire, and then, yeah, of course, this registration will be also proportionally longer. So I think we can look at this a little bit more in practice, how these messages look like, and just a little bit of this tracking script, how that looks like, and maybe that makes it a bit clearer, or maybe it will pose more questions. Let's see. Okay, so here we are. I just arrange the screen a little bit. So it's a little bit cramped at the moment because it's on my laptop screen. Normally we have a huge 4K screen for the microscopes, but hopefully it's visible. I just have this test sample in the microscope. It's just a needle. So nothing interesting. It will not drift at all. So you just have to believe me that the script works. I just wanted to show you how these messages look like in the API. So to basically interact with the microscope in a more of a manual way and check what's going on, we developed this Lux logger. So this also comes with every microscope. And normally customers don't use this, but if someone's interested, we show them. And here you can set up the MQTT connection settings and basically publish to whatever topic you like and subscribe to any topic. So this hash is actually a wildcard, so to subscribe to any subtopic that's under this main serial number. So for example, now if I would go here to turn on the 488 laser, then you can see that this, because we're subscribed to all of the subtopics, you can see the message from the GUI. So this was published to the serial number /GUI, and this is the actual message here. And so this is type device, and then the device is the laser, and you send the command to set the laser to true and 40% intensity. And then there's a reply to the embedded /lasers topic. So this is coming from the microscope control hardware. And this just confirms that this is now the new state of all the lasers. So here it includes everything, and then the 488 is now in this new state. And so now, for example, if I would just copy this message and send it by hand and change it to false, and if you look here, when I send it, then it turns off the laser. So hopefully the concept is clear. Basically, you can just click around, see all the messages, and then copy it in your script, and then build basically any pipeline that you can think of that's basically supported by the GUI. So as long as you can achieve it by a sequence of GUI clicks, you can see the messages, and your script will need to parse the incoming messages from the components, mostly the microscope, and send the messages to control the microscope. All right. So for the tracking, this one is in Python, but as I said, it could be any language. We just used it because most people know Python, and we also use this if someone wants to control our microscopes. We usually send this to them as an example, so they understand how the communication works and how to set up a basic pipeline. So we have a configuration file which is loaded first, and here there are some basic things, like how to connect to this MQTT broker. Then some information about the geometry of the stages. This is important to map the pixel or the voxel coordinate shift to the stage coordinates. And it's a pretty old script, so we don't really need it because you could read it actually from the metadata of the images, but we still have it here. And then maybe these are more interesting because you can set up multiple section channels. So maybe just for those who are not familiar with the Luxendo microscopes, the way it works is you set up a channel, and the channel means basically every setting that you have is stored except for the stages. So here, for example, I have the camera settings, laser, scanners, timing, etc., filters. Those are stored in this channel, so I can add more. I have 3 channels, and then the stack would define the position of the sample that you want to image. And when you set up an event, then you have to basically create this pairs of stacks and channels to define the experiment. So you can have like a series of different stacks and channels. So I just wanted to explain this for the settings, because you can have different channels for the same stack. For example, like this, if you do multicolor imaging, you want to select which one should be the reference channel, because you don't want the tracking to look at both of these and then send conflicting information about the position of stack 0. So here you can just specify which channel should be the reference. Normally you select the one that has the most content, and then which camera should be used as the reference, the same as for the channel. For multi-view systems, maybe you have left and right camera, and but the tracking only needs to use one of those to do the registration. And then you can specify what should be the minimal shift to correct. Of course, there will be some noise, so you don't want to correct every little jump. Yeah, so this would only send a message to the microscope if the shift is more than 10 microns. And sometimes the registration can go wrong, and then you have some really big jump and you want to avoid it. So you also have this maximum shift that can be corrected would be 100 microns in this case. And then of course you can change it depending on your field of view, what makes sense. And this is what you asked about, Rafael. You can also configure like how often should this registration run, so every time point or every second, every fifth, whatever. Yeah, exactly. So then once this configuration is loaded and parsed, connect to the MQTT server or to the broker. For this, we have this small helper library to deal with the most common type of use cases. I will upload both of these to the GitHub, but I don't think I have time to explain what this MQTT service does now. And then
sorry, but in a nutshell, that is just like a translator, right?
yeah, I mean, basically what it does is because mostly this is asynchronous, right? So you send a message and then you don't know when the reply comes. And then what this service does, it gives you some helper functions to synchronize this. So if you expect the reply, then it has like, for example, this method called publish check reply, and then you can define which topic to publish to, what's your message, where do you expect the reply to come, and then you can provide the function, callback function, to check this reply. And then depending on the function, then you will get true or false, and then you know if you, for example, you want to set the laser, and then you expect the reply to have the same laser settings that you configured. Then in this check function, you can do some parsing to make sure that the laser is what you expect.
All right. So it's not only taking care of the messaging, it's taking care of checking for the replies and therefore the synchronization.
Yeah, exactly.
Okay.
And then this one is a bit simpler. It just waits for the reply and then returns the reply string. Right. So mostly we use these two, and I think yeah, otherwise it's a bit complicated to deal with these. But you still need to do everything asynchronously and use these callback functions because you don't know when the message will come to certain topics. So so when you do this subscribe, then this MQTT library that's under this service, it just registers it as a callback function. So for example, here with this, you can subscribe to this embedded /execution topic. And this is the callback function on execution. So basically when a message comes to this topic, then this function will be called. And a message comes to this topic when I start a new experiment. So for example, if I now start run and I stop recording because there's a lot of things going on, then we have a message here coming from the embedded system that now to this topic that I just showed, that now it's under the scheduler control. So scheduler is true and scheduler is running. So basically, and then when the experiment stops, then you have some other flags set in here. So in this on execution, what you would do is just check if the scheduler state is running. And that means that the new experiment was started, and basically just clear your tracking status in this case. And when the new image is recorded, so if you go back in here, that is published to this data cameras topic, and then you can call this post stack on post stack function. So here, I don't know if you guys are familiar with this partial construct in Python, but basically this on post stack has multiple inputs, and with this I just make a new function that already prefills some of the inputs of that function from the configuration file. And so I include like 4 parameters, and then I think the message is still empty. So basically, what this does is it returns a new function with just one input parameter, which is going to be the message, and all the others are just fixed to these coming from the configuration file. And then here, there's a little bit more, but basically it's mostly just parsing the JSON messages and the file path, and checking if these are coming from the reference camera and the reference channel, and then you check this stack ID, and then because you can have multiple positions, multiple samples for each stack ID, then we start a new tracking instance. So here I just instantiate a new tracking instance for the stack, and if it's already running this tracking, then it will just process the new incoming image. Yeah, this is a bit much, I know. I'll upload all of this, as I said, to the GitHub, and you can have a look at it. And yeah, maybe we quickly look at this process new images. I think we still have like 5 minutes.
At least from my side, very interesting, so don't apologize.
So the input here is the new image path, and I think the self. So basically, it's this tracking instance. It stores the previous image path, the channel stack ID that you have with some base directory. Yes, so it's kind of just to keep track of the state of what's going on, and also a copy of this MQTT service, because it needs to send a new message to the microscope to change the stack. And then when the new image comes, yeah, it does some parsing and basically passes it to this registration method. So yeah, unfortunately, this is a very old script, so I didn't find the actual registration script, but I don't think to understand the whole script, I don't think it's super important what this thing exactly does. Yeah, basically it just returns a tuple of 3 coordinates x, y, z that has the shift between the previous image and the new image. And once you have the shift, it just prints it out so you can see that it all worked. Then it checks if it's bigger than this minimum shift. If not, it doesn't do anything. It just skips it. And otherwise, it just keeps track of the cumulative shifts since the start of the stacking. And then, no, okay, sorry, if it's more than this maximum shift, then it's an error condition, so that's why it just returns. And then if everything was good, then it keeps track of the cumulative shift, because if in the previous time point it was not big enough, for example, then it has to keep track of the shift of the previous, and then it just adds it all up until it's bigger than what you configure in this minimum. And then it updates the stack, and basically what it does is just constructs a new JSON message from the stack ID and then the stack coordinates, and then sends it to publishes it under the GUI topic. So it just fakes it as if it was the user interface, and basically the microscope picks it up and updates the coordinates. On the next time point, it will take the stack at the new coordinates.
So in the beginning of the experiment, there's only one stack added to the list of acquisitions, and then they get added iteratively.
Sorry, what do you mean by that?
Sorry, so you just add the new stack to the list of next acquisitions, and you don't like update the stack position to be acquired that was initially set.
So the stack list is defined in the user interface, and so you can just have as many as you want. And then the script keeps track of each individual stacks in this tracking instances. So basically for each stack that you defined in here, the script will start a new tracking, instantiate a new object of the tracking class and keep track of them in here. Is this what you meant, or did I misunderstand it?
Yeah, maybe I misunderstood wrong. So when you sent the JSON message after tracking, you said you add a new stack.
No, so basically what this update stack, right? This one. Yeah, so the command is add stack, but it actually, if you also provide the name, it will update the existing one. Yeah, sorry.
Okay, got it.
It's a bit confusing. Yeah.
Got it.
If you don't give it a name, then the microscope will just create a new stack for you. But if you provide the name, then it knows, okay, this was already there, and it just replaces the old one with the new coordinates. Yeah, I mean, if we run it, then basically it just connects first, and I just have a time lapse. Maybe we just do one stack for 4 repetitions, and I think the first time point just finished now, and yeah, I think I just messed up the config, because here I'm only recording the left camera, but I have the right camera as the reference. So I start it over. But yeah, I think we're out of time, so we don't have to look at it. Yeah, okay, so now it starts the tracking. This is the first time point. And then every time a new stack is finished, it does the alignment. So yeah, as I said, it in this case, because I didn't find the actual registration script, it doesn't. It just always returns 000. But yeah, the reason we don't really have this properly anymore is because we fully integrated it to the user interface, so it's a bit simpler to use, and people don't really need to. If someone just wants to use this tracking, they don't need to deal with this Python script and JSON files and stuff. They can just configure it here. So these are all the same configurations that I showed you before. But we keep this script more or less alive just to demonstrate how to talk to the microscope through Python.
And then
Yeah.
And then I guess because you have access to the user interface, you say it's a website, and potentially, you know, if I would have been doing this tracking thing and I want to add it as a UI unit, you can also kind of connect UI to this script somehow.
Yes, definitely.
Okay.
So I think if we look at this one, so you can connect to any of these components with your script. So each of them will have their own topic. Of course, you will have to subscribe to the appropriate topic to receive the messages from the data, for example, or from the image processor. Then you can control each of them. Yeah, I mean, we do have some documentation how this works. At the moment, it's not public. I'm working on it to convince the higher ups, but yeah, hopefully it will be soon.
Very cool. Thanks, man.
Okay, yeah. So I think that was it from my side. We're